For our problem, we have chosen the integrable pegs problem. The problem we are trying to solve is that we are given 11 holes and 10 pegs which are laid out in a line. We want to interchange the black and white pegs, but there are only 2 permitted moves allowed. We are able to move the pegs into an adjacent empty hole or jump over one peg into an empty hole. Can we make the interchange? What is the fastest way to solve this problem with the fewest steps? We'll start with a simple example of the problem. When we first attempted the puzzle, we started with a smaller number of frogs and tried various different sequences of moves trying to find a solution, some of which left us in a position where no more valid moves were available to be taken. Soon enough, we've realized that this leaves us in a position where no more valid moves were available to be taken. This conjecture is invalid. By reflecting and learning from our previous mistakes, we start thinking ahead and moving one step at a time. This helped us realize that having 2 frogs of the same color right next to each other at any spot other than the beginning or the end of the puzzle is detrimental. For our second conjecture, we'll try to avoid 2 frogs of the same color being right next to each other. We'll move frogs of the same color in an alternative pattern. With this, we are able to find a solution that involves keeping the colors in an alternating pattern, allowing them to jump past each other to the end. Here are some working examples. To prove that this conjecture was the fastest way to solve the problem with the fewest steps, we checked if we could possibly increase the amount of jumps taken, which would decrease the amount of steps, as a jump covers 2 spaces and a shift only covers 1. In our current strategy, every frog either jumps over or is jumped over by every frog of the opposite color. However, this would cause 2 frogs of the same color to be directly next to each other in the middle of the puzzle, thus making it unsolvable. Therefore, there's no way to increase the amount of jumps taken, so our original conjecture is proven to be the most efficient solution.
Next, we expand this to see how many steps it would take for n frogs on each side. To do this, we created a chart which displayed the ratio between the number of steps and the number of frogs on each side. By looking at how many steps it takes for 1, 2, 3, 4, and 5 frogs, we were able to detect an equation for the given series. By analyzing the pattern, we came up with the conjecture that for n frogs, it will take n squared plus 2n steps. This is because when we took a closer look at how many jumps and how many shifts it would take to solve the puzzle, given any number of frogs, we found that there were n squared jumps and 2n shifts, so the equation for the total number of steps is n squared plus 2n. While our conjecture is found to prove true, the provided equation of n squared plus 2n is useful for future use while making the question much easier to explain. Finally, with this equation, we felt it has greater use in helping students conceptualize factoring and expansion,